OK, so now we can start talking about performance of our networks. And there's two main thoughts I want to get across here, or two really good ways to measure our networks. When we were talking about performance here, we were talking about parameters, rather, of the topology. Now we're going to look at the overall network performance. First thing is bandwidth. So bandwidth is the rate of data that can be transmitted over a given network link divided by amount of time. OK, that sounds pretty reasonable. Latency is how long it takes to communicate and send a completed message between a sender and a receiver in seconds. So the unit on this is seconds. The unit on this is something like bits per second or bytes per second, so amount of data per second. These two things are linked. So if we take a look at something like bandwidth, it can actually affect our latency. And the reason for this is if you increase the bandwidth, you are going to have to send fewer pieces of data for a long message, because you can send it in wider chunks or faster chunks or something like that. So it can actually help with latency. It can also help with latency because it can help reduce your congestion on your network. Now, we haven't talked about congestion yet. We'll talk about it in a few more slides. But by having more bandwidth, you can effectively reduce the load of your network, and that will decrease your it'll decrease the load in the network and decrease the probability that you're actually going to have two different messages contending for a same link in the network. Latency can actually affect our bandwidth, which is interesting, or rather, it can affect our delivered bandwidth. It's not going to make if we change the latency, it's not going to make our links wider or our clock speed of our links faster. But it can make the delivered bandwidth higher. Now, how this can happen is, let's say you have something like a round-trip communication. You're trying to communicate from point A to point B back to point A. And this is pretty common. You want to send a message from one node to another node. It's going to do some math on it or do some work on it, and it's going to send back the reply. And if you can't cover that latency, if the latency were to get longer, the sender will sit there and just stall more, and it'll effectively decrease the bandwidth of the amount of data that can be sent. Now, if you are good at hiding this latency by doing other work, that may not happen. You may not be limited by the latency. But there's another good example of this is if you are worried about end-to-end flow control. So a good example of this is in TCP/IP networks, something like our Ethernet networks. There's actually a round-trip flow control between the two endpoints, which limits the bandwidth. And it's actually tied to the latency, because you need to have more traffic in flight to cover the round-trip latency. And this starts to be called what's called a bandwidth delay product, where you multiply your bandwidth multiplied by the delay or the latency of your network. And if you increase the latency, the bandwidth will effectively go down if you do not allow for more traffic in flight before you can hear a flow control response. So you'll see this if you have, let's say, 2 points on the internet and you put them farther apart and you have the same amount of in-flight data, or what's called the window is the same. The bandwidth is going to go down as you increase the latency. But if you were to increase the window, it would actually stay high, because your bandwidth delay product. And the reason for that is you'd be waiting for ACKs to come back from the receive side. OK, so let's take a look at an example here to understand these different parameters. We have a 4-node omega network here with 2 inputs, 2 output routers. Each of these circles here represents input nodes, and these are the output nodes, and they basically wrap around. They're the same sort of thing. We have little slashes here, which we'll represent as serializers and deserializers. So what this means is you're transmitting some long piece of data, and it gets sent as smaller fits, if you will. So we're sending, let's say, a 32-bit word, and it gets serialized into 4 8-bit chunks across our network, across the links, because the links in the network are only 8 bits wide, we'll say. And in this network, we're going to have our latencies be non-unit. So let's say our link traversal here, each link here takes 2 cycles, takes L0 and L1. And our routers take 3 cycles, R0, R1, and R2. And to go from any point to any other point in this network, you have to go through 2 routers and 1 link. So we can draw a pipeline diagram for this. So for a given packet, we can see, let's say it gets split into 4 fits here of the head fit, 2 body fits, and a tail fit. We start in the source, and we send. Well, it takes 3 cycles to make a routing decision through here, 2 cycles across the link, 3 cycles across one of these routers here, and then we get to the destination. And if we look at this in time, it's pipelined. We can have multiple of these things going on at the same time. So we have the next flits 1 cycle off or 1 cycle delayed. And the reason we want to draw this is we want to look at what our latency is for this sending this one packet. Because it's a little bit hard to reason about, because we're effectively have a pipeline here, and we're overlapping different things. And we'll see that one of the things you would think would be up there doesn't show up down here. So first, let's take a look at this. We have 4 cycles here at the beginning, which is just our serialization latency, or the length of the packet divided by the bandwidth of the packet. If you were to increase the bandwidth here, the serialization latency would go down. Then we have time in the router, which is our router pipeline latency. So it's 3 cycles here, and another 3 cycles in the second router. And if we have more hops, this will go up. And then 2 cycles here for the channel latency, which we'll call TC. So we can see that it's the summation of all of these different latencies is our latency. But what's interesting to see is that there is no deserialization latency here. So that's the one that's missing. And it's because we've overlapped that. Because it's pipelined, we're counting that in the serialization latency. Questions about that so far? OK, so now let's take a look at our message latency and go into a little more detail here. If you look at our overall latency, which we'll denote as T, it's the latency for the head to get to the receiver. So that's all of this stuff here, plus the serialization latency. Now, T head has our TC and our TR and the number of hops, but it also has something here that is a contention, which we haven't shown. So in this network here, there was no contention. This was an unloaded network. There was not multiple nodes or multiple messages trying to use one outbound link or use any one given link in this design. But that can happen. Let's say these 2 nodes here send at the same time, and they both need to use this link. You're going to get contention. And that will increase our latency. But if we rule out the contention for a little bit of time, we'll start to see the unloaded latency here. And we just decompose this into sort of subcomponents here, that we have the routing time times the number of router hops that we need to go, plus the channel latency times the number of channel links we need to hop across, plus the serialization latency. And the reason we decompose this is this lets us reason about how to make networks faster. So we can see that there's a couple different ways to make our networks faster. First thing we can do is we can make shorter routes. That'll decrease both these uppercase h's here. The reason I have two different uppercase h's is as you can see here, in this example, we basically went two router hops and one link hop. Usually they're connected, though. If you have to go farther, you need more links and you need more router hops. You can make the routers faster. So you can either increase the clock frequency of the routers. You can make them wider if they take multiple cycles. Now, if they're already sort of as fast as you can go, it may be hard. You might be able to increase the clock frequency somehow, but it could start to get hard at some point if they're already wide channels and wide muxes and have a fast clock rate. Faster channels. So if you're going between multiple chips, usually you're limited sort of by the signal integrity of the communication links between the different chips. And this sometimes even happens on chip. So you have to think about that going to a higher clock frequency could be problematic. But if you make a faster channel, your latency is going to go down. And then finally, this is our serialization sort of cost here. We bake into it here either wider channels or shorter messages. Maybe you have a lot of overhead on each message. You have a really big header for the message. If you try to shrink that, that'll make your network go faster and reduce your latency just by sending less work or sending less data. But that may not always be possible. But a good example of this, if you look at something like TCP on top of IP networks in sort of our internet class networks, people have proposed a whole bunch of revisions to that where they try to sort of squeeze out some bytes or use some sort of encoding standards to reduce the amount of data in the headers, because TCP header is pretty long, for instance. And you already see a good example of that. They actually have an optional field in TCP headers, which is typically not sent, thereby reducing that in the common case. OK, so now let's talk about the effects of congestion. So what I drew here is a plot of our latency versus the amount of bandwidth that is achieved, or offered bandwidth. And this is for a given network. So it's pretty common that as you increase the bandwidth that you're using at any given network, the latency of the network goes up because you start to see more congestion in the network. So the probability that any 2 points are contended for will go up as you get closer to the maximum amount of maximum achievable bandwidth in the network. Now, there are some networks that people build where this is not the graph does not really look like this, or does not look like that. So for instance, if you have a star topology, you don't have any congestion. So you're going to get something that looks much more like an ideal plot here, where you sort of have a straight line and another straight line. Because as you increase your load on the network, everyone can send to everyone else. So there's not going to be any congestion in the network. And I have a few lines here that sort of show interesting things that sort of hack down at this. So in a perfect world, you'd have your zero load latency. So this is the latency of the unloaded network. And as you increase the bandwidth, it wouldn't change on our unloaded network. And with and if you had no congestion in the network. But we start but that's not usually what you see on real world networks. A couple other things sort of also decrease or increase the latency and decrease the bandwidth of a network. Usually you have some routing delay that gets introduced into the network, and that's going to basically push us away from higher bandwidth and lower latency. So you want to be farther down on this plot because that's lower latency. And also, if you have flow control in the network, so local flow control, that also looks like some form of congestion. It'll actually slow down your network in certain cases. But I just wanted to give you guys the idea here that for any real-world network, it usually looks something like this. As you get closer and closer to using the whole network, using all the bits available by the network, the latency starts to shoot asymptotically through the roof.